Hopefully, it is restricted by the. Yeah, everyone's
okay, well then I started the recording, so let me welcome Alex from Zagreb, and he will talk about localization and homotopy theories. Thank you very much for this course.
Hi, thank you for having me. It's a pleasure to visit Brno for the first time. And I should say before we begin, I promised this will not be a beamer talk, but I ran out of time. So this is a beamer talk. Let me move the pointer out today. Yes, so I'll talk about a part of the three-dimensional gauge theories. Actually, not just three-dimensional, we just invented the Arvanitakis generalization, and how you localize them in a normal way. So the main point of the localization, what I want to talk about, is that you can do a localization calculation for a non-supersymmetric field theory, which is also in addition non-topological. Of course, you can localize topological field theories because they don't have local degrees of freedom. So it only really counts if it's non-supersymmetric and has local degrees of freedom. So that's the interesting part. So this class of theories, which I call Manin gauge theories, because of a specific ingredient that goes into their construction, they generalize. First, we wrote them down in 3 dimensions, and I will stick to 3 dimensions mostly for the talk. They generalize 3-dimensional Yang-Mills, Friedman-Townsend theory, and this more obscure theory called the third wave, which Paul Townsend, Alex Brown, and myself wrote down in 2015, and I will briefly describe it later. That's it, and all of these are non-supersymmetric, in at least not in the usual way, and I will explain what this funny evanescent supersymmetry is. If you wanted supersymmetry, but on-shell, there are no on-shell superconductors, so it's honestly speaking, as far as the Hilbert space is concerned, we don't have any fermionic states, any superquantum states. So it's a rewriting of n equals 0. That's why it's interesting. You can look. Yes, I don't need to talk. Okay, so without further ado, let's start. So most people have probably seen Chern-Simons theory. Here, A is a 1 form and some 3-fold and 3. It's valid in some of the algebra. And here the wedge product is implied. Okay, and I've made explicit what usually is called a trace here, kappa, because this is a situation where non-cyclical gauge groups will be necessary, and in that case, there's multiple forms you could have in there, and that choice will actually turn out to be important. Okay, so yes, as I say here. Typically, we write trace up to some constant, but it will serve us well to let it be more dynamic. Now, as it happens, the supersymmetric generalization of this, which was written down by, I think, originally Ivan, a while ago, is it's notable because while you do have lambda hat gauginos and a couple of scalar fields, sigma and d, to close the supersymmetry algebra, you see that you can integrate them out by their own equations of motion. So this is manifest. You can integrate out sigma and d together. You can integrate out lambda hat together. Oh, and there's the square root of the determinant of the metric. That's awesome. So this n equals 2, in fact, and by the way I wrote it, this is for Euclidean supersymmetry. I'm interested in Euclidean field theories because these are the ones you can localize. Because you need things to be positive definites. Yes, so this has n equals 2 Euclidean supersymmetry, standard gauge multiplex transformations. However, it's manifestly equivalent to the non-supersymmetric n equals 0 theory. So, for example, you can calculate observables exactly, at least some supersymmetric observables for turn signings. For example, partition function with or Wilson loop insertions, as long as they're supersymmetric. And that was not really a mystery, because back when people did this sort of calculation, which was in like 2009, 2010, because they say, well, it's not a mystery that we can localize this theory, which is non-supersymmetric, because, well, it's a topological field theory, it doesn't have any local degrees of freedom. So the novelty will be introducing degrees of freedom into this, essentially. And so for the purposes of distinguishing honest supersymmetry to supersymmetry which relies on things which are zero on shell, I will call the supersymmetry which disappears upon integrating out evanescent. So this theory does have evanescent supersymmetry in this sense. The supersymmetry transformation of A, for example, is proportional to one of the fermions, right? And the fermions are zero on shell. This is what I mean by evanescent supersymmetry. Some people would have called this trivial, but for marketing reasons, I chose one. Okay, so here is, so this is mostly for review to illustrate the utility of the localization method. So if you haven't seen this before, the Ostermatt-Heckman formula gives you an expression for the integral over some symplectic manifold M2D of well, this integrand. Here H is some Hamiltonian function in that manifold, and omega to the D omega is the symplectic form raised to an appropriate power. So you get a top form here and a scalar. So it turns out, and those mathematicians found out differently, more complicated, right? This is a sum over the zeros of the Hamiltonian, and there's a proportionality factor, which you can view as arising from, you can view it as a one-loop determinant. And that's a very cute, there's a very cute supersymmetric localization. So you can take this, and you can say, okay, this is actually the exponential of omega d. And we just keep the top form part. And then you can put both of these ingredients in this action expression, where the x's are essentially dx's, so the differential forms. And this is invariant under these supersymmetry transformations if there was a geometric condition which I seem to have forgotten. But anyway, so this is invariant under these supersymmetry transformations. And so XH to the Hamiltonian, yes, of course, this is the condition. So XH to the Hamiltonian vector field associated to H.
You went to sleep? After sleep?
Oh. No. Oh, that's going to be a problem.
Do you want to plug it in power somehow?
Yes, maybe. Give me a second. I should know that. Plug. Okay, nothing is overheating. Very nice. Okay, now we can do it. Yes, so the supersymmetry transformation is determined by The confirmation of the fermion is the Hamiltonian vector field associated to H. And when that's the right-hand side, then this S is invariant under the supersymmetry. And then, say we pick an invariant metric, G, and if the integral curves of this vector field are compact, so generate circles, then such always exists, right? On an average. Then we can just deform the action this way. We take Gij Ci times the Hamiltonian vector field, and then we hit it with a Q. So when you do hit it with a Q, the bosonic part of this just comes from Q hitting C, then we get the norm squared of the Hamiltonian vector field. And you can prove immediately that this is invariant under this, if you rescale this field, if you adjust this real parameter lambda, because things that are too exact are too total. So this is lambda independent, and if I take the limit where lambda goes to 0, this is the norm squared of the Hamiltonian vector field, so the expression is only non-zero where the Hamiltonian vector field vanishes. Otherwise, you get e to the minus something positive times infinity, right? Okay, so then this is the way you get the sum over the zeros. And you get the rest of this expression by actually doing the path integral over the C's carefully, and you get determinants. Say quadratic path integral inference. Okay, so this is the supersymmetric proof of the Ruđer-Heckman localization formula. Some details have been omitted. And this is also how localization works in general, and this is in particular why I want to do Euclidean field theory. What replaces this Gij, and which needs to be Euclidean, is going to be a metric on some bundle of fields, and that needs to be positive. Because otherwise you take the limit, or this number goes to infinity, and then you get e to the minus infinity and some e to the plus infinity, and then it doesn't make sense. You can't do.
Can you maybe spell out what would be go wrong? You go one slide back and you talk about Everson supersymmetry and non-Everson. What would go wrong in a non-Everson supersymmetry when you integrate out the superpartners compared to here?
That's the point. If it's not evanescent by definition, you can't integrate out the superpartners.
You can always integrate.
I mean, if you have a theory with local difference.
Oh, okay. So you can talk about it classically.
No, I'm also talking about it quantum mechanically. So say you have a theory with supersymmetry. Typically what happens is for every boson degree of freedom you have a fermion, right? And you also see this in the Hilbert space. Yeah, but I guess you want an action. So I guess you mean classically. I mean in terms of the action. Yeah, so evanescent supersymmetry is only something in the path. Okay. So it's when you have a theory which doesn't, let's say the Hilbert space only has bosons for such theories. Okay. And yeah, so this is the general logic of how localization works. It works the same as in this example. And I produce this example because this is also an example of evanescent supersymmetry. If you look at the C equation in motion, it just says omega I Jx and J equals 0, so C is 0 on shell. So this illustrates that even if the supersymmetry is there is only classical clear in the path integral, you can actually get something out of it. So we already have nice examples. So the real question is, can we get examples which are not, zero-dimensional matrix models, essentially, like the previous example, or topological field theory? And the answer is yes, we can. Yes, we can. So in 3 dimensions, the point of our work was just that any theory in this class of Manin gauge theories always enjoys this evanescent supersymmetry and it enjoys localization. Let's describe this class of theories. So the action is given by a Chern-Simons term. Now I wrote the gauge field as a double struct A. And it's perturbed, well, it's deformed by a mass term. It's quadratic in A, so it's some kind of mass term. And depending on a specific kind of what we'll call a mass matrix, which acts on the Lie algebra where this double A takes values. Okay? Now, the point is this. So as I wrote it, if M is generic, then you break all of the gauge symmetry, and then you have nothing about, I don't know, Chern-Simons model theory. But if you pick M to be a specific matrix and for a specific kind of Lie algebra here, FRAP, you can ensure that you retain gauge invariance under a sub-algebra or a subgroup, if you want, of this Lie. This is the factor D, by the way. So if you wonder what this is called, it's going to be. So I will call the actual gauge symmetry, the one that survives this mass perturbation. I will denote it G. And essentially, this double struct gauge field will split into two parts. It will split into some auxiliary thing. I will call it tilde, and then an unadorned A. I will call the honest gauge field that is in there. Yes, so what are the other ingredients? So it depends on the Chern-Simons level. And there's a constant G squared with units of mass, and this must go here just by dimensional analysis. And because there's a coupling constant already, you see why this seems like it's going to have degrees of freedom. And there's a bilinear form on the big algebra T, which I will call eta, because in general it will not have Euclidean signature. Okay. Oh, and also, of course, the mass term depends explicitly on the metric. Here's the square root that. Maybe I should even. Do we have a map? Yeah. So I might. Yes.
Maybe choose another one because this one seems to.
Yes. Oh, yes.
That's amazing.
Yes, so this is a square root that G A nu G nu up to some combinatorial constant. All right. So you got the action here, convenience.
And where was it in the expression?
Oh, the M I forgot to write it. Okay, you can put it here. And that's only one of these. Yes. So, oh, and I mentioned the Lie algebra. Right, so for which mass matrices acting on the big algebra G do we have G gauging values? So you do the straightforward calculation, it's a one-line thing. And the condition is just it must annihilate that part of big A, double struct A, which lies in the subalgebra G. And we also have this form of adjoint invariance, or the bilinear form that you get by hitting N with the form eta. And that is it. This is some way, this is the way, in fact, you can assure that you have the gauge symmetry you want. And all of these assumptions sorry, including also the assumptions that eta has split signature, which you need to actually preserve parity. Because remember, most gauge theories, at least the ones that we care about, do preserve parity, whereas Chern silence by default does not, unless, for example, well, unless you define parity to also act on the gauge field. And this is only possible if the gauge group is not simple. In particular, you need eta to be split signature.
So eta has two entries. So it acts on two things, right?
Well, let me write it out. So this is D, and you can write it non-canonically as a sum. The B filter, right? And eta restricted to G. Eta restricted to filter is equal to 0. So here, G and G tilde is not commute under the bracket.
Right. But then, okay, so eta act on.
So eta act on this.
But I would assume that eta is like when you say it's a pairing and so on, then it actually two things, right?
Yeah, two complementing.
Yeah.
Yeah.
So and there's a comma between the two entries. But why? How does it act on the up there? There's no comma.
Oh, you can put a comma there or there,
Okay.
and here you can split apart. This is
Okay, that's implicitly understood.
Yeah, this expression is special because anywhere you put the comma, it's unambiguous.
Right. And in fact, I would have assumed the same with the kappa you had before, because I'm thinking of kappa as a killing form, like form, and also has two entries.
Yeah, exactly. You can lift these things to universal enveloping, I think is the general statement. But yes, that's how it's binding here. So in particular, let me be explicit. Let's set k to 1. So you have eta a comma a plus 2/3 a squared plus g squared. What am I doing? Yes, it's g squared star and a. So with all of these assumptions, in particular that eta is split signature, G is anisotropic for eta, and G is maximal. So the maximality comes about because, well, if it's not maximal, then basically you have all of these gauge symmetries anyway, so you kind of have to go maximum. If you want. So with these assumptions, the pair of G and D form a Manin pair, or G is what's called the Dirac structure.
So are they two? These are simply two different names for the same thing. Is that
essentially? So Manin pair and Dirac structure are the same. And Lie quasi-pi algebra simply means it's the same, except you've chosen a specific complement, G tilde of G in D. Okay, so they're the same for almost all intents and purposes. Oh, okay, good. Right, so I should say here, if G is simple, notice G can be simple, but D need not be simple. In particular, we'll see that D can be G cross G. If G is simple, then you can prove that admissible mass matrices that satisfy these properties can be, for example, the inverse of the killing form, extended by zeros in this complementary part G2. Okay, so there's a few examples that we can use. Looking for the time. It's already good. There's a few examples which will be relevant. So we choose generators TA for G, and then we extend to generators to the big algebra D. So you take also some D tildes. Because eta is isotropic on G and G tilde, you only have a non-zero pairing between these two subspaces, so you get delta here. And these are the commutational relations for any such pair. But really, at least as far as this talk is concerned, I will simplify things by essentially showing beta to 0, which is to say there's no Lie bracket in G tilde, but there's this cubic term. So you see the T close into a Lie subalgebra. That's what you want. Here you get, with this term 0, you get the semi-direct product of T and T tilde, of G and G tilde, and this is 0, but then you generalize so that G tilde needs not close into a Lie algebra. So the case where it actually does close into a Lie algebra, so this is 0, we have the semi-direct product of G with its dual, and then eta pairs G with G star in the opposite way, and this will be the Manin pair that corresponds to Yang-Mills theory, we will see in a second. And there's two more interesting cases. One is where D is two copies of G, left and right, and then you take eta to be the difference of the traces on the left sector and on the right sector. And this is a construction that we've seen, for example, from string theory. If you look at ABJM gauge theory, it has a gauge field, which for reasons of narrative preservation has a gauge group, which is the product of two copies of UN, one left, one right. And the Chern-Simons level is the difference, and this is the way that theory maintains gauge invariance. In the same way, this theory will maintain gauge invariance. So this will give rise to the third wave theory, for those who know what this is. And there is also a mystery example where instead of having G left cross G right, you have the complexification of G as the bigger group. And it appears, it looks a lot like the third wave theory, but for negative complement. I don't really have any comments on this, knowing we haven't really investigated it, but it looks like a healthy theory, because we proved that all of these theories are healthy, and we'll elaborate what this means. Okay, so let's do some explicit examples. So under the conditions I gave earlier, for the Yang-Mills case is the triangular Manin pair. That's the name from the mathematics community. They named these for having different considerations in mind. So that's the case where we have the semi-direct sum of G with G star, and we feed these structure constants into this action. So this cubic term is where all of the structure constants of D enter, because this term will be, of course, 1/3 AA. This is the bracket in D. All right. So we feed all of these choices of structure constants in, and the assumptions on the M matrix mean that these are the non-zero matrix components for M. Now the up and down indices on A and A tilde are, one is in G, the up index is in G, the down index is in G. Okay, and we have also split the gauge field into which one here? A is A plus A tilde, corresponding to this. And then out comes Yang-Mills in this first order formulation. So this double gauge field has the honest Yang-Mills gauge field inside, this is A, and then the A tilde is the auxiliary field, the first order formulation. And the role of the mass term is to allow us to eliminate A tilde. So you see explicitly, you eliminate A tilde, you're going to get A tilde is star F, I think. apostrophe F. And then you integrate that out, and then you get F star F, which is the usual Yang. All right. And instead of trace, I have the MA and just an indexable way of writing it. Okay, so the other example, which is interesting, is the third wave gauge theory, which some of you are interested in, I understand. And it comes from the Manin pair, which is where the big algebra is two copies of G, which commute with each other. And this G tilde is essentially the anti-diagonal subalgebra in the two copies. Sorry, the anti-diagonal space in the two copies in the sum of two copies of G. And I say space and not subalgebra because the anti-diagonal is not closed unless the algebra is abelian. Okay, so you do the same procedure. You substitute the structural constants implied by the fact that G has a decomposition into two commuting copies of the same algebra. Then out comes the Lagrangian we wrote down in 2015. And I can even illustrate how this preserves parity. So this preserves parity by, well, you do a parity transformation of the Chern-Simons terms, they pick up a sign, but then you flip left to right and right to left, and then these trade places. So you've picked up two minus signs, and that's how you preserve parity. And for this theory, it's more obvious why it's parity preserving. But in both cases, you have to send A tilde to minus A tilde. It's just that this A tilde thing is expressed differently. And I don't have time to elaborate on why the third way theory is interesting, except to point out that it's a non-Lagrangian theory in the sense that you can eliminate, for example, A right using both equations of motion for A left and for A right, which gives you an equation of motion that you can prove cannot arise from any local gauge invariant action. So this you can show it doesn't satisfy the right hand side does not satisfy the invariant density. So it does have a non-ist action, but you need two gauge fields to do it. Anyway, so I already made this point. And I should say at this point that besides these three examples, there's a whole zoo out there, which is given, for example, by solutions to the modified classical Yang-Baxter equation that some of you may have heard in the context of integrability. Now, as to if these norms are integrable, I have no idea. I don't know what integrability means in quantum gauge theory, to be honest. But we haven't investigated whether there's a Yangian symmetry or something like that. Right. So what else did we do in this paper? Besides the localization, which I will get to, we also showed that these theories are healthy, at least in some respects. Firstly, you can calculate the Hamiltonian in terms of the canonical momenta and the canonical positions, which are the space parts of the gauge fields. And I should say some of this A tilde turns into canonical momentum. It's quite nice that way. You can see this already because this term A tilde dA is going to be generic. So you get a time derivative for A here. So that's a field, and then some bits of A tilde are going to be the moment. That's very nice. So the Hamiltonian is manifestly non-negative, practically speaking, which is good, at least it makes sense. And there is reflection invariance, which is say parity invariance, for a wide class of Manin pairs, at least the ones which have this F tilde structure constant equals 0. And a reminder that F tilde is the one that goes here. So it's the structure constants for G tilde if it were on the algebra. And for semi-simple G's, this is always true that you can arrange for this without loss of generality up to field group definitions. And there's a very nice proof using the AKZ formalism, which I can't really summarize right now. But essentially, if you use Chern-Simons as an AKZ field theory, you find that canonical transformations from that perspective actually generate shifts that take you from one admissible G tilde to another one. And then this can be used to set these structure constants to zero. Quite a lot. And these theories also enjoy reflection positivity, which is the unitarity in Euclidean signature. And by this I mean specifically that if you do hybrid transformation and orientation reversing isomorphism on one of those, then the action is complex conjugated. In fact, I arranged that the action is real. Okay, so for example, the partition function is at least formally guaranteed to be non-negative. That is one implication. And this remains true for the evanescent supersymmetric versions of these theories. Okay, so without further ado, this is how you supersymmetrize it. So some of these terms are familiar from when I discussed equals to Chern-Simons. So you have the Bosonic Chern-Simons term, have this term here, lambda lambda hat minus sigma d, which we store for n equals to Chern-Simons, and lambda lambda hat are the G-nos, and they're valued in the big algebra D. Sigma and d are scalars, and they're also valued in D. The big algebra D is happy. And there's a simple addition we need to make involving the mass matrix here to ensure that this remains supersymmetric. So the sigma scalars just get their own little mass term.
So can you stress that it's Euclidean supersymmetry? So I guess it's Euclidean signature?
Yeah.
So when you say that the Hamiltonian is found from below, is there any issue with going with equation?
That's a good point. So actually, this calculation, this was done in Lorentzian signature. So I say I'm mostly interested in these theories because I want to do localization calculations with them, but the Lorentzian version actually does have, it's a Lorentzian version that has non-negative management. Yes, maybe I should have pointed this out in this slide. Okay. Right, so I claim that this theory enjoys supersymmetry under a deformation of the usual n equals to Euclidean supersymmetry for the gauge multiplets in 3 dimensions. And that deformation is given by this new term over here. So the rest of the terms we get, two kinds of supersymmetries, one which transforms one lambda and keeps the other fixed, and vice versa. And I've written it for the transformation that transforms lambda hat here. Okay, so we see which transforms lambda. We see lambda hat is constant. For A goes into, so zeta is the spinor. I wrote this for flat space-time, a flat space. Zeta, gamma, lambda hat. Lambda is a two-component spinor, so this is, the contraction is vector, which is very good. And everything is the same as it was before I introduced this mass deformation here and here. The only difference lies in the transformation of the fermions. And you could have anticipated this given the form of the action, because what does this action do? So you can still integrate out lambda and lambda hat by their own equations of motion, and you may still integrate out d and sigma by their equations of motion. So this term, if you want, gives you an extra contribution to the sigma equation of motion, which you can solve for d. That's fine. So it's equivalent to the n equals 0 Manin theory, if you want, which is just this first term. But then the transformation of the fermion is different, and it has to be different because, well, notice that every line, so this one, and this one, the right-hand side depends on lambda, which is 0 on shell, which is good because this is a symmetry that only permeates the. This symmetry that only exists because we introduced objects which are trivial on shell, or evanescent, if you want, for marketing reasons. But here, the same must be true for the variation of the fermion. The variation of the fermion is a boson, and the boson equation in motion is master formed. So you get, there's an F slash here, that's the field strength of A, right? But the equation in motion for A, the bosonic one, gets an extra contribution because of the mass matrix, right? It's obvious from here. And this is exactly the extra contribution you get. And there's also a contribution due to the, well, I don't know what to make of the sigma here, but apparently you do require it. I don't have such a nice explanation. But sigma is anyway on shell 0 as well. So there's no consistency in writing this. Okay. So on these transformations, right, so we see for n equals 0, we get exactly the standard n equals 2 supersymmetry. And in that case, the standard supersymmetry is also an evanescent supersymmetry, which is, say, the right-hand sides here are 0 on shell. But if we want to introduce local degrees of freedom, we necessarily have a deformation of the supersymmetry such that it remains evanescent. That's another way to see this. And we also see that all purely bosonic supersymmetric observables remain supersymmetric for any power of the mass n. By purely bosonic, I mean ones which depend on A, for example, this Wilson loop. And the transformation of A doesn't change under this mass formation. So this supersymmetric Wilson loop, for example, remain supersymmetric. And the partition function will is also something that we can calculate using this supersymmetry. The difference is that there are more local observables that are gauge invariant under the subalgebra G of the big algebra. For example, MA transforms like a tensor under G. It's not obvious. You have to use some of the magical algebraic properties that M does, that M satisfies to show this, but you can take contractions of MA with itself and then have new local observables, which is what you want, because this is a theory with local degrees of freedom, and so it had better have local observables, right? Well, unless it's gravity, I suppose.
Normally, in a supersymmetric theory, we say that there should be, if you have local degrees of freedom, there should be the same number of bosonic and fermionic.
Yeah.
That's not true.
That's right.
So you pinpoint exactly how you evade that.
Yes, so the point is that all of the transformations here vanish on shell.
Yeah.
And so the super partners can also be integrated out, so that's consistent.
Right. Yeah, I understand that it's consistent in this case. Is there some general understanding of, or do you know other examples where this happens, for example?
Other examples. Well, we're trying to construct some like higher dimensional generalizations of this.
Mm-hmm.
And well, we constructed the Manin theories, but we haven't done the supersymmetry yet. But I think you can probably even prove that you can always deform the supersymmetry this way. It's just I haven't done it. But I gave some examples. For example, if you want something that's not a Chern-Simons theory, this is another such example. Right? It's a finite dimensional theory, of course.
I mean, can you imagine something even more exotic where you have both local bosonic and fermionic degrees of freedom, but their number is not equal?
Yeah, of course. Of course. So you can probably add honest fermions to this. And wait, not even probably. No, I have done. We have done some matter coupling. Well, it's in my notes. actually. So I did that. And you can couple scalar fields here, you can couple fermions here if you want. And you can still have evanescent supersymmetry. There is, so the thing that changes, and you can infer this from the reasoning I gave here, the thing that changes is because, and I'm talking about matter that is coupled to the gauge field, because otherwise who cares? If it's coupled to the gauge field, then there will be an extra contribution to the gauge field during the motion. Let me just get locked. Yes, so if you want to couple some matter, essentially there will be a current that you need to add here to maintain supersymmetry. So for example, C B plus A double square. See here, actually it's not even need B double square. It can be single structure if memory serves. Actually, you do want mass. You do want to do this. So that's. You can write this down. So this double struct A will get a contribution to its equation of motion. So there is a term that's quadratic in fermion, so you add here, and then it remains supersymmetric. You can also do it with scalars. And with scalars, you even have to have a term involved in sigma for reasons that are somewhat unclear to me, but that's how the algebra works.
And is this supersymmetrization always unique?
Oh, I doubt that.
Like, for example, I mean, the first term you would have guessed from the Channel sequence was this G square sigma star and sigma.
Oh, this term is uniquely determined. So if you have the whole rest of the action, and yeah, this was how we found this term. So at some point, well, basically we wrote this and this term, and then tried to deform. I eventually reasoned that we need to deform the transformation of the fermion, and you deduce that this term is necessary for the MA because of this has a non-zero supersymmetry variation, the AMA term. And yeah, you also end up getting a non-zero supersymmetry transformation. So how does this work? I don't quite remember how it works, but I remember this term was determined uniquely. So I think if you specify your offshore field content, then the supersymmetry is determined, but not if you don't, if that makes sense.
Is there any understanding that why it has to be sigma? So, for example, without the mass deformation, it kind of, like just the supersymmetrization of the Channel sequence, it kind of looks like sigma and B, the two scalars are equal.
Yeah.
Right. But then somehow with the mass deformation, one of them must appear with the mass term, but the other one doesn't. So, like, is there an understanding that why one gets favored over the other?
Yeah, I think maybe. Actually, I think this is a point that speaks to just supersymmetric Simon's theory, not necessarily this. I think the multiplet here should not actually be thought of as coming in with a factor with the square root of the determinant of the metric. I think D should be thought of as a top form instead. And the same should go for one of the gauginos. Because, you know, it's still a Chern-Simons theory and it's metric independent except for, you know, framing effects when you have a Wilson and so on. So if you formulate it that way, then it's easier to see that you can't have a quadratic term in B. yeah, that's the. I think that's all we answer. Okay, let's move on. So, yes, so I said you also want to fix the supersymmetry algebra. And by this, I mean, I'm only interested in a very specific part of the supersymmetry algebra. I'm interested in the part where the supersymmetry transformations square to 0. So here, by delta zeta, I mean these transformations, but you act twice with the same zeta. So zeta is some spin. Okay. So delta zeta squared is 0, and delta zeta hat squared is 0, and this is true for all mass matrices. Now, in the term silence case, the honest term silence case, where f equals 0, the anticommutators involve translations and gauge transformations. And for the n equals 0 case, this is all you get. But for the case where you switch n on, notice you necessarily must get this term here again, because this vanishing is the equation in motion for A. That's how we have consistency. And the interpretation of the full symmetry algebra, actually, it's not clear whether closed is the anticommutators between zetas and zeta hats actually close to a finite dimensional thing. But we don't really care, to be honest. We just need something that squares to 0 to do the localization, like we were doing here. Right? And so we can proceed and do what was advertised. Was that a question? Right. So I wrote the supersymmetry transformations for Euclidean space. Actually, you need something compact to avoid things exploding. If you want, you need something compact as an infrared regulator. But there's very little difference. If you do it on a sphere, at least, there's very little difference in the supersymmetry transformations or the action. So you get an extra term. What do you get? You get some terms involving the cosmological constant, the sphere radius somewhere here. It's not very much. Okay, so want to localize with respect to the delta zeta supersymmetry. So we look at this expression. So we're going to localize on the locus where this vanishes. So to do that, we need something like a gauge fixing fermion, such that you take a supersymmetry variation and get something positive definite. So I'm mentioning here you can always arrange to get something that's positive definite in this. So you get something, you get a bilinear form in the Lie algebra D, and you can average it along the gauge orbits and then get something that's positive definite. Well, you start with something positive definite, but probably non-invariant, and then if G is compact, you can average it, then out comes something positive definite and G invariant. And then you write down a localizing term, whose bosonic part by construction is the norm squared of the right-hand side of the fermion supersymmetry transformation. And then you do the localization argument. You add this delta, zeta, epsilon, this term to the action. And then you rescale zeta so as to go to minus, so that the prefactor of this term goes to minus infinity. And then we only get contributions from where this vanishes. And you do some gamma matrix magic, and you find out two equations. The two equations are essentially the 0 and 3 form part of this, and then the vector part. The 1 and 2 form parts. So D is eliminated in terms of sigma, and we get an equation in terms of A and the scale of sigma. So we have two independent fields. We get A and we get sigma. So notice at this point already that we get essentially the field equation for the theory, except in this contribution of the sigma scalar. And this curly D is just the covariant derivative with respect to A. And by the way, I think this is an Lagrangian equation as well. Just because of the D sigma, like I didn't try to prove this, but I can't write down Lagrangian that actually gives rise to justice with the D sigma. Right. So I want to turn this into an integral over A alone, the path integral. So actually, so I didn't specify the observable. Yes, so you can localize anything that's supersymmetric invariant, for example, an appropriate Wilson loop. On the sphere with the supersymmetries are wrote down, so this will be a great circle. And you can see this because if you take a spinner on the sphere, you can form a bilinear, which will be a vector. And any Wilson loop that's supersymmetric invariant, you better be invariant under the translations produced by that vector. And obviously, that will be an isometry, and the isometries of the sphere then just lead you to great circles, right? Okay, so you can take derivatives of this and get an equation that allows you to eliminate sigma. Under some favorable cases. So for the third way theory, this works exactly as I'm writing it, technical reasons. And for Yang-Mills theory, this works, and you can integrate out sigma. That's why I mean by this works. Sorry, you can solve this for sigma. That's why I mean by this works, with some modifications. And this allows you to solve for sigma up to sigma 0 modes. And by 0 modes, I mean ones where curly D double struct sigma 0 is equal to 0. Okay? So the space of such 0 modes is in fact finite dimensional. And physically, it corresponds to gauge transformations which do nothing on the gauge fields. So they only exist for specific gauge fields, which say for specific connections, which are called reducible. And they correspond to subgroups of the gauge, specific subgroups of the gauge. So all such 0 modes, finite dimensional. Right? You can also see this if you want, because this equation is elliptic in sigma. So there better be a finite dimensional space of 0 modes. Okay, so 0 modes settled. For the non-zero mode part, you go to wait, where is it? You go to this equation, you substitute the solution for the non-zero mode part here, and then you get the moduli space for A, which we're meant to integrate over. This is the solution to what would be the equation of the motion without supersymmetry, the n equals 0 equation of motion for the Manin theory, plus a current which arises from the solution for the non-zero modes in terms of the Green's function and so on. So with all of that said, we've taken a path integral that was originally path integral over A, sigma, and lambda hat, and D, and then we've reduced it to a path integral over this moduli space, solutions to this equation for A, and the path integral over a finite integral over the 0 mode sigma. And remember, D is already solved in all cases, so there's no integral over that. So, which is something that does appear like it's still infinite. Well, I don't know if it's finite dimensional or not. So this equation, I suspect it is infinite dimensional, just by BDE analysis. But it remains to be proven. But certainly we get an integral over solutions to a nice PDE in A, so it's a much smaller space, even though it's infinite. and then times a bunch of integrals over zero nodes, which are finite dimensional, which looks like a significant simplification compared to the full identical. Oh, and I've omitted the ghost. The fermions only contribute a one loop determinant, which is in principle calculable. And you get this determinant from by expanding this in terms of this expression as the supersymmetry variation of the gauge fixing fermion. So it's not a gauge fixing fermion, but it's closely analogous. So there's going to be terms which are quadratic in lambdas over there, and these give you a determinant, and it looks like a Dirac determinant plus extra stuff. Right. So as a sanity check, we set n to 0, and we look at these equations. We indeed get that star f is equal to 0, so both of these terms on the right-hand side vanish. And the j term vanishes because this is when n equals 0, we just get a Laplace type equation for sigma, doesn't have solutions. Or the solution is sigma equals 0 for the non-zero groups. And so star f is 0, which is to say f is flat. And then if f is flat, then solutions to this become solutions to this one, d sigma 0 equals 0. So sigma is constant. And then we get the known localization results for n equals 2 times minus 3. So at least what we're doing as a sanity check, it does reduce to what is known for the theory without a mathematics. Okay, so we also did the generalization to theories in higher dimensions, at least we generalized part of the picture. So we wrote down an analog of what should be a Manin theory in higher dimensions. And we haven't supersymmetrized these yet. And the main reason is just that you have to pick a dimension to do anything with pairs. That's just it. So we just wrote down the bosonic theories. So the general structure is that you take the topological field theory for some gauge field. In general, you have to take an AKZ gauge theory. And you add a specific mass term. So the mass term takes the same form as before. So you have M acting on well, if you want the vector space of some L infinity algebra now instead of the Lie algebra D. And because it's an L infinity algebra, you don't just have a binary bracket. Here that was meant to be a mu I. So mu I takes arguments, takes multiple arguments from 1 to 1. Yes, so you have a collection of higher brackets.
So I equal 1 is a 1 bracket.
That's right.
So wouldn't that term actually would talk to the last? It would be quadratically like the last term.
Yeah. So yes, I confused myself earlier today because I thought we made an algebraic restriction such that this would not arise. But then I could not find it in the paper. So all of the explicit examples we displayed have the 0 mu 1. I think you can arrange for this to be true. So we want the target space L infinity algebra to be concentrated outside of degree 0. And then I think for degree reasons you can arrange mu 1 to be 0. But I'm not quite sure right now. Certainly all of our actual examples have mu 1 0.
Or are you in some sense working with a minimal infinity where the mu1 will be 0 anyway?
Actually,
Yes, those are the best examples.
but that would be mu 0.
But mu1 here.
So mu 1 equals 0.
And if you use zero equal to zero, that's non-flat or something like that.
Yeah, that's right. So mu1 takes one argument, and mu0 takes nothing. Yes, that's right. No, we restricted the minimum ones. Yes, okay, confusion resolved. Yes, so you want minimal infinity algebras that are concentrated outside of degree 0. So this just gives you L infinity algebras, minimal. Okay, good. Yes, so in general, you can prove, or there's an elegant proof that this expression is gauge invariant under L infinity algebra gauge transformations. And my co-author, Hyun Kim, and this wrote a very formidable calculation where he displays a class of L infinity algebras with L infinity subalgebras G, which are the generalization up to homotopy, if you want, the concept of the Manin pair, such that you do have gauge invariance under an L infinity subalgebra. So this mass matrix does preserve some gauge invariance, like we had in the mentioned. And the examples that fit into this scheme, this admittedly somewhat arcane scheme, include, so we have an integral Yang-Baxter two-dimensional signal models. You get these from taking a Poisson signal model, which is a topological field theory in 0 dimensions. But wait, does that have a 0, 1 bracket? I think it does, actually. It's really confusing. So you take the Poisson signal model, you add a specific mass term, and then out comes a Yang-Baxter deformed two-dimensional signal model. It's a very short calculation, actually, once you've set up all of the notation dimensions, etc.
How do you get, it looks like the action you wrote is valid in all dimensions.
Yeah, so this is in all dimensions.
So how do you get a two-dimensional Yang-Baxter? So by Yang-Baxter sigma, you mean the Yang-Baxter deformation of the principal parallel, or?
Yeah, so I can show you, I can be explicit because I have the paper. Not the one. Here we go. Right, so right, so we start with this model. So this is the AKZ topological field theory, and the target is essentially the shifted cotangent bundle of the lead group G. We want. And then the big algebra is G plus G star. Okay, so you get, actually this is the case where you do get a 0 form field. So G is a scalar field valued in the group, and then A is a 1 form valued in G star. So if you want, G takes the values in this subalgebra in terms of this analogy here, and then A is in this G field. And then pi hash is the Poisson tensor. So that is essentially pi, yes, pi ij, ai, aj.
Okay.
This way. Okay, so we call the metric here a Hodge structure. I prefer to call it a mass matrix, but time is not food. And you just let me scroll down. So the mass term that you can add turns out to be, because this mass matrix obeys various algebraic identities, right? Because gauge invariance is not guaranteed if you just write down its matrix. So you get a straightforward mass term. This is just A squared in terms of A. You integrate A out, and then you get the action for what's called the Yang-Baxter signal model. So here, this is the, what is this notation we use? Here that's meant to be 1 over 1 plus pi. Well, you've seen the what more, right?
What does the star mean there?
I think
There are two different stars.
yeah, I think this is what we mean. Jake. I think that's what we mean.
Okay.
The talk, it will let me. Right. Yes, so it includes this kind of theory. A theory called, written down by Broccoli and Jaeger and Stefan Tyson, called the third wave B-form stage theory in higher dimensions, which seems on relative. And also Yang-Mills in any dimension. So there is the version of Yang-Mills which algebraically it looks very similar to what I wrote earlier, and I can illustrate where it wasn't. Yes, so here D is G semi-direct G star, but in general you have something like D is G shifted to, I think shifted to D minus 3, where D is the space-time dimension. Semi-direct. How does the counting work? Okay, it's shifted to be in some degree. And you know, you turn the crank with this choice of infinity algebra. And it turns out, so for this case, it turns out to be a greater than the algebra. Shift. And then out comes Yang-Mills. So it does fit into this, Yang-Mills does fit into this higher dimensional Manin scheme. And of course, it comes out in its first order formulation. Right? So there is, you know, we do fully expect that we can localize four-dimensional Yang-Mills this way. But what we would like for the future, of course, is to push this calculation forward and see if we can actually get some exact results out of it. I forgot to say some things on this slide. So all of these theories, every theory in this class is seems to be healthy, at least in the sense that you can calculate the Hamiltonian straightforwardly. And for the Lorentzian signature theory, it's non-negative, which is at least suggests that there's no instabilities, classically speaking.
So what about the supersymmetry? You didn't say anything about supersymmetry.
Yes, that's because we haven't chosen one of these to start turning the crank on. So we're kind of doing something else, and then we'll repeat. But yeah, as I was saying, I think that the general logic is dimension independent. So we write down the supersymmetry, for example, for the Yang-Mills version of this.
But you expect there to be a Yang-Mills version which has supersymmetry?
Yeah. Yeah, of course. So there's a Yang-Mills formula, sorry, there's a Manin formulation of Yang-Mills. And then the game is to deform the supersymmetry transformations appropriately. Which means
you would start with the usual super Yang-Mills and reformulate it in this language. But
that's right. So the supersymmetry, this evanescent supersymmetry will not be the usual Yang-Mills. That's right. Because the right-hand side needs to be zero on shell.
Right.
And you know, there's going to be some variance with an F on the right-hand side.
But you expect there to be a version of this evanescent supersymmetry, or
yes.
Okay.
The evanescent.
Because that's what you need somehow for that. localization.
That's right. Yeah, I mean, if it's on a supersymmetry, you can do exact calculations and get those using supersymmetry, but this is, we've known this for many, many years. So that's
Yeah, somehow you want to work with non-supersymmetric theories.
That's fine.
They'll have some kind of supersymmetry.
Sorry, Alex, can I ask you about this probability form-based theories?
Yes.
So I'm trying to reconcile this with our result that if you just take Bošković license equations of motions, then just those equations of motions doesn't lead to tree-level amplitudes, which has nice factorizations of the phase and unitarity. So the claim, I mean, how to reconcile this with what we're saying here?
Oh, I thought the theories have a range, right?
No, not the preform theory that they wrote down, right? So they wrote several ones, right? They had P forms and the P-1 forms and etc. Talking about, I mean, the P-1 form suffer from even worse factorizations. But even just the P form ones, like the equations of motions had third-way consistency, but their whole argument was that these equations of motions can't be all Lagrange equation for some action. They don't satisfy the integrability condition and
Yeah, like, what did we compare to? There's this. Ah, here's the pointer. And then just give me a second. Oh, here we go. Only I could see where my pointer is. Ah, yes, I don't have the internet. Okay, just a second. Yeah, I thought we had theory with. Do you see my point?
no.
Okay, now if you,
Yeah.
here we go. Yes, it gets stuck on the edge of the screen. Right, so I think we had it. Well, we compared with things which had action, so now I'm confused. Yeah, where is this? Right, yeah, so this is the broccoli theory. It might be one of their models, right?
But all of their models they claim analogy. All of the equations of motions in that paper.
Well, we seem to have found a Lagrangian. Hang on. Ah, how did we do this? Okay. So we have another thing simple expression. And then D is this one's first. Now it's going on with the circle, where it should be. Granted. Yes, so we claim that this action gives rise to the broccoli equation theory. So,
and you want to wait. So this is not the this has two forms, right? B and
so A is a 1 form, B is a P form, B tilde is a D minus B minus 1 form, and A tilde is D minus 2. We're in dimension D.
okay. I don't remember an equation of motion in the paper which had this structure. They had one which was like 1 D minus 2 form, and then they had one which is one p minus 2 form and one p minus 3 form. I mean, one I mean one category. I mean, these are all here as well.
Okay.
And then they propose that there is a generalization where you have p minus 2 form and p minus 2 minus some n form. But that they did not pursue. They just wrote down a candidate equation of motion and they didn't pursue it.
Okay.
That's the only two. But this is some sort of extension of that structure. I could see that, but this is definitely not one of the equations of motion that's stated.
Okay, good. It's good. It's good you pointed this out. So we fix this. Okay, so then we should probably say we have a generalization of their theory. Okay, what is this? This was an old version of the slides. Yes, okay. Okay, yes, so apparently we wrote a new theory, wrote down a new theory compared to. Okay, now I'm confused. I thought we had literally the same. Okay. So, yes, all such theories are healthy and they include at least young nodes. Going back to the theory, both of which are interesting. So we're quite happy. And this is essentially the end of the talk. So just to recap, the point is to try to do supersymmetry without superpartners, but try to use this in such a way as to extract useful localized expressions for quantities of interest, like the partition function or correlators of whichever observables happen to be evanescent supersymmetry. And you can even do this for Yang-Mills theory and some of its funny generalizations in 3 dimensions. So we have pursued this program as far as the localization is concerned in 3D, to extent. And it remains to do this in other dimensions, notably 4-dimensional Yang-Mills, and also to do to calculate things in full, because there's a bunch of, you can calculate things in terms of one determinant, but not. But getting explicit expressions requires some sophistication. There are some simplifications. Yes, because of evanescent supersymmetry, which need to be carefully considered. And I have some speculation about theories which are defined in terms of dual Manin pairs possibly being dual themselves. For example, what is a good example? So Friedman-Townsend theory is dual in this sense to ordinary Yang-Mills theory. But we don't know at the moment whether there's a duality in a useful sense, which, for example, would send observables calculated in one theory to observables calculated in the other theory. That's something we are also thinking about. And yeah, that was it. So thanks for sitting with me.
Questions or comments?
So can I ask one more question? Okay. So in 2+1, I mean, fractions in 2+1D, you had this, I mean, there was this possibility of novel Higgs mechanism, I think it was called. So is there something analog of that for the Manin formulation, then would you expect there is some sort of novel Higgs in for this higher dimensional generalization?
Right. How do we do the novel Higgs mechanism?
Oh boy.
Yeah, I mean, you would expect that you can maybe a couple of scalars and try to fix them, and then there would be new contributions because of because of the structure of the theory. So I guess ordinary Higgsing would correspond to the Manin pair, the triangular one. That's what I called it. And then that novel Higgs mechanism in our old paper from 2015 corresponds to the polarizable Manin pair. And there presumably is an answer to our general Manin pair, but I didn't consider this until you just asked it. But I don't see an obstacle.
Yeah, I think that would be quite interesting as well, because there would be new phases of the Higgs theories that are interested.
Yeah, but I should say that the only one of the 3D theories that you can get from a Higgs mechanism, from introducing this mass via Higgs mechanism, is, I think, is the third wave version, where you have G cross G. Because in that case, so remember that this eta, which is a bilinear form of big algorithm, is split signature. And if D is simple, then all forms are going to be split signature. But if D is G cross G, then it emits a Euclidean, a positive signature thing. And so this mass matrix can arise from the minimal coupling of scalars which have positive kinetic terms. So there's within this class of theories this theory of which Yang-Mills is the limit. They're even more special. But in general, you can't get the mass finished by Higgsing, because then you would be Higgsing scalars with non-positive definite kinetic terms.
How special is this evanescent supersymmetry? I mean, did you try to analyze this more generally? How restricted is it?
I don't know. I think you should probably be able to get this in all cases. You can just introduce things off-shelf.
You mean by all cases? Any theory or just the class of theory?
I think any theory. I think the real question is whether you can introduce it while retaining, for example, unitarity or reflection positivity, parity invariance, positivity of the Hamiltonian. So I think that's the less trivial part, which is not automatically guaranteed to be there.
And is it also pretty clear that how much evanescent supersymmetry you would get? Like whether the completion would always be equals to 2, or it could be equals to 1, or could be.
Oh, I have no idea. Yeah, this is another reason why we should do the theory in general dimension, or at least dimension different. Because it's not in D equals 3 Euclidean, and equals 2 is minimum. For Lorentzian, of course, you can have n equals 1, but we don't have an appropriate reality condition for Euclidean spins. So n equals 2 is minimum. But in other dimensions, I don't know. I guess even in 3, you could ask whether you can do evanescence n equals 3 supersymmetry.
And can you somehow have an evanescence SUSY, which is, I don't know, the level of SUSY is local, but even the local SUSY is evanescent.
Like supergravity.
But I mean, it's evanescent somehow.
I don't know yet. I haven't really thought about it.
But it seems like to completely invalidate the usual argument that we expect the number of physical degrees of freedom, bosonic and fermionic degrees of freedom to match.
But I mean,
here, more or less all examples.
But here by design, like the superpartners, they might appear on chip, right? So it's kind of
yeah, but if you could do this generally, that why have we observed in every example?
I mean, it's essentially enlarging the off-shell field content, such that off-shell field content somehow has this nice structure.
Technically, if you want 3D supergravity, this is already the case, because you can integrate out everything. Those are
Yeah.
So that's one example.
Yeah.
But if you can actually do, example of local degrees of freedom this way, I don't know, I guess it remains to be done.
And the speaker, once again. From the recording, but we can continue on the session.